Hi everyone, welcome back for another heat and mass transfer or transport 2 video. In my past couple videos, we have looked at how to derive the total heat diffusion equation in Cartesian coordinates, which related to a cubic volume, and then we also looked at how to do cylindrical coordinates, which related to a cylinder. And now today we're going to look at spherical coordinates to see how this relates to a sphere. So we're going to be deriving the heat diffusion equation for a sphere first. And secondly, we are going to simplify this equation that we derive and simplify it if it's a steady state problem with no heat generation and only in the radial direction, which is also what we did for the cylindrical example, or for the, cylindrical example as well. So I want to show, these are notes from my other part of the video that are just on the back here, but this is what I've written today. This is just our agenda. I'm going to move my lamp a little bit over here to hopefully help with, does that help at all? Not really. Let me point it up a little bit. Alright, so I think that slightly helped. Now you can, there we go. Now you can see what I have written here. Actually, let me move this over this way. Alright. So it's a little bit dark, but if I hold it close, hopefully you can see that okay. The lighting is kind of bad in here, unfortunately. I'll just try to tilt it over towards my computer. Okay. So first, we're going to start with looking at a sphere. So we're going to draw our three different coordinates here. So a sphere is obviously a 3D figure. So we're going to have our x, y, and z directions. So I just have my axes labeled like that. And then each of these three directions is going to have a different direction associated with it, so it's not going to necessarily be x, y, z. But since we're looking at a sphere, we're going to have, if you remember from the cylindrical example, we had r and d theta and z. But since this is a sphere, so now the whole thing is circular, we're still going to have our r and theta, but this time we're going to add another angle in there called phi. So that's going to encompass the entire sphere circular shape, rather than the cylinder, which was drawn out, had a certain length associated with it. Now we're looking at two different kinds of angles, phi and theta, and the radius r remains the same as before. So I'm going to go ahead and draw, we're going to have our theta is going to be projected between the z and the y plane. So I'm just going to write that here, and then our phi is going to be between x and y. So I've just drawn some sort of projection in between those two planes that you're going to see. So you're going to imagine that those are not necessarily along the z and y plane. Those can be anywhere in that 3D form, but I'm just drawing it out that way to get a better visual. To make it a little bit easier to think of. So right now we're trying to figure out what our volume is going to look like. So if you remember before, in cylindrical, it ended up being r d theta dr dz. So this time we're still going to have our dr like normal, and as we recall from before, the theta had to be multiplied by r in order to get it in correct units. So that is still going to be applicable here. So r d theta, because theta is in radians and we need it in meters or the same units as the dr, so that this is all in the same units. The same problem is going to be shown for phi as well, but it's going to look a little bit different. So I'm going to try my best to draw this. So we're going to have our dr sticking out from this line that I've already drawn here. And then I'm going to attempt my best to make this as easy to see as possible. It's kind of just hard to picture because it is like a 3D shape. And I'm also, just to be completely honest, pretty terrible at drawing 3D shapes. So I'm trying my best to make it look not terrible for you guys here, but that's essentially a chunk of what our volume is going to look like. So that's a piece of our sphere. And as you see from that bolded line where the dr is, so that's our change in radius, whether we're looking, up until this point here or this point up here, that's our change in length and radius. And then for our d theta, that d theta piece is actually going to be along this side here. And then our change in phi is going to be this length here. So the d theta is going to be that arc length right there next to dr, and then the angle between the top piece, that top floating piece, and the bottom piece is the d theta, so how that angle is changing. And then in order to get, or sorry, d phi, not d theta. And then in order to get phi in the correct units, we're going to multiply it by r sine phi. R sine theta d phi. And the reason why this is multiplied by r sine theta is because our phi is all the way down here. So in order to relate it to this piece up here, we're going to need the sine of this to get this angle here. And then we have our d phi still like normal. And then the r, once again, is there to get it in the correct units. So this is going to be our volume piece. So so r squared, it's going to end up being, because we have the r from the d phi and r from d theta, so r squared sine theta dr d phi. And that's going to be our volume term. So we can go ahead and begin plugging this in for our energy storage piece. So as we recall, energy storage is that rate E dot st is how it's typically written. And that's going to be our density times heat capacity, temperature, change in time. So once again, energy storage is going to be a rate, so it'll be time dependent. So we'll be looking at the density of our object, its heat capacity, and temperature at a certain time. Then multiplied by our volume piece. So I'm just copying our volume that we found right there. R squared sine theta d theta dr d phi. As definitely a mouthful. So now we can go to our energy generation term. So this is going to be the same process as what we did for the Cartesian and the cylindrical coordinates. So we find our energy storage, energy generation, and then the net heat flow in each direction. The only thing that's going to change is our cross-sectional areas when we plug it into Fourier's law, and then obviously our volume here has already changed. So now we're going to look at energy generation. So that is E dot gen. That's equal to our heat flow. So the Q dot rate times volume, R squared sine theta dr d phi. So this is our energy generation term. We have that Fourier's law, or not Fourier's law, the Q dot, so that's the heat flux times the volume. And then now, the other part that we're missing from our heat diffusion equation is the net heat flow in all three directions. So when you're looking at net heat flow, you're going to have Q is equal to the heat flowing in minus the heat flowing out, as we recall. So Q in minus Q out. And now we're going to look in each direction. So once again, we're going to use our Taylor series expansion to find the Q out. So that's when we extrapolate information we know at a certain position in order to find information we want to find at a position further along that function. So QR, actually I'm going to dictate this as net heat flow again, the way that I did in the other videos. So NHFR is going to equal that Q in minus the Q out. And now we can plug in the Taylor series expansion for Q out again. So it'll be Q in minus, in parentheses. If you recall from before, the Taylor series expansion just takes the heat flow that we have in plus change in heat flow, and we are looking in the R direction right now, evaluated at dr equaling R times dr once again. So this piece in particular should look familiar to you. We're doing the net heat flow in the R direction, Q in minus Q out, and then plugging in for Q out the Taylor series expansion of Q in plus change in Q over change in R, evaluated at the change in R equaling R times dr. So once again, this is taking the value of the position we know, which is Q in, and adding the change in the function leading up to the position we want to find, multiplied by that change in length. So that's the dr there. So we can simplify this. We get the net heat flow in the R direction being negative dq at R over dr times dr once again. And once again, this is not unfamiliar to us. This is what we know from past videos. So we can go ahead and do this for the theta direction. And if we just skip all those steps, dq theta, d theta times d theta again. And then same thing for our phi, net heat. Net heat flow in the phi direction equals negative dq phi over d phi times d phi. So that's what we get for our net heat flows in all three of those directions. And then, as you recall, we take this information and we plug in Fourier's law into each of these Q's in order to get what our Q is going to be. And then we also have to sub in the cross-sectional areas for each of these directions as well, depending on what our volume ended up looking like. So now we have our total equation, which is the energy storage rate equals the net heat flow in the R plus the net heat flow in the theta plus net heat flow in the phi direction plus the energy generation term. So that's the definition of our heat diffusion equation right here, and we can go ahead and start plugging things in. For right now, I'm going to leave the energy storage and the energy generation just written as the EST and EGen, just because it makes it a little bit easier for when we're simplifying the net heat flows. So energy storage equals, and then let's plug in our net heat flow in the R direction. It's negative d over dr. Plus negative d over d theta. Plus negative d over d phi. plus E gen. So I've just plugged in each of our terms right now for the net heat flow. And now we're going to go back to Fourier's law. Q equals negative K A dt over d, whatever kind of variable we are analyzing for there. So now we can look at what our QR, Q theta, and Q phi are for each of these directions and plug that into our full equation and begin simplifying from there. So I'm going to flip to the next page just because it's running out of paper, and we're gonna need a lot of room for this simplification. So Q equals negative Ka dt over d, whatever we're looking at. So QR, that'll still be negative K. That will not change depending on what direction we're looking in. And then our cross-sectional area for the radial direction, so that's going to be the d phi times d theta. But as we recall, these are not as simple as just being d theta and d phi. We're going to have to do these two whole values here in order to get the cross-sectional area, because we do need this to be in the correct units of meters squared, and you don't get that unless you add these r's in here too. So it's going to be, cross-sectional area will be r squared sine theta d theta d phi, and then times dt over dr. So here I've plugged in that cross-sectional area. The r sine theta d phi is one direction, and then the r d theta is another direction, and then still just times our dt over dr. So that's what we get for the r direction for our heat flow there. Now we're going to look in the theta direction. So once again, negative K will not change. And we'll go back to our little piece here. Now we're looking in the theta direction, so we're going to have the dr and d phi left. So that'll be dr times r sine theta d phi as our area. R sine theta d theta, d phi dr as our area, and then dt over d theta. But we have to add an r here with our d theta in order to get it in the correct units. So that'll be dt over r d theta. So I plugged in our area here. R sine d phi is one direction, dr is the other, and then we have to add our r d theta in there to get that in the correct units. And then you'll notice that r will nicely cancel with the r in front of the sine. So we can simplify this even further, cancel those r's out, get negative K sine theta d phi dr dt over d theta. Now for the phi direction, negative K once again remains the same. We look at our phi direction, we'll just have dr d theta left, so dr r d theta will become our cross-sectional area. R d theta dr is our cross-sectional area, and then dt over, and then once again we need to add the r sine theta onto the d phi in order to get that in correct units. So r d theta dr, r sine theta d phi, and we can cancel the r's out once again. Negative K d theta dr dt over sine theta d phi. Alright, so now that we have the Q's in each of the directions, or the heat flows in each of the directions, we can plug that back into our master equation. So now let's go back. I'm going to write our energy storage and energy generation in their entirety now, because we're going to be looking at how we can cancel out some terms and simplify this a little bit. So the energy storage rate is going to be density, heat capacity, temperature over change in time, times our volume term, r squared, sine theta, d phi, d theta, dr, and that's going to equal net heat flow in the r direction, which we'll recall is the negative d over dr, times whatever our QR is, which we just found, so we can plug this in, negative k r squared sine theta d theta d phi dt over dr, excuse me, times dr. So, okay, that probably sounded like a lot. So here we have our energy storage. This is the same as what we found earlier. Now we've plugged in for our net heat flow in the r direction, negative d over dr. This whole term is our Q. So QR that we found right here. And then the final dr. So I'm going to go ahead and flip back. So what we had written here, we had that negative d over dr, qr, dr. So we just plugged in the qr, which made that term look way bigger than before. So we're going to do the same thing in our theta direction, in phi direction. So plus negative d over d theta, negative k. We found our theta, or our q, to be the negative k, sine theta d phi dr times dt over d theta. Sorry, it was d phi dr, not d theta. And then times the d theta once again, plus negative d over d phi times the q phi that we found, which is negative k, d theta dr dt over sine theta d phi times d phi. Alright, so this is what I've written to plug in for our q's. So that term right here is our d theta, so net heat flow in the theta direction. We just plugged in what we found up here. Sorry. And then the final d theta, and then same with the d phi over here. So we have the d phi, and then our q phi, which we found up here, and then the final q or d phi at the end. Now we're going to add on our last piece, which is the energy generation term. Plus energy generation, which we found to be q dot times our volume, r squared sine theta d phi d theta dr. We're going to follow a similar procedure as last time and cancel out the volume. So let's cancel the volume here and here. And then so I've canceled out the volume in our energy storage and energy generation. And now, so what happens with our QR right here? So since this R is within this, this piece right here, and it's being evaluated, the dr, so the derivative of this r is being taken of, we can't take it out of here because it's not considered a constant. So we can cancel that sine theta out because theta has nothing to do with this dr, but this r squared does. So we can't take it out, and we have to just divide by r squared on the outside. So we can cancel these three terms out. The dr we can cancel, yes, but then we can't take this r squared out of that parentheses. So I'm going to go ahead and start rewriting. So we canceled the sine theta, d phi, dr. But now we're going to have negative d over dr, negative k. Still within there, the r squared dt over dr. But since we couldn't cancel that r squared out, we have to divide by r squared because that was still in our volume term that we had canceled out before. So now we have 1 over r squared on the outside there. So that 1 over r squared has to happen because this r squared was canceled out, so we divided everything by r squared, but this one can't be removed because of the dr. So we're going to go ahead and continue in the other directions. So we'll see for the theta, this sine theta cannot be removed because of this theta. But we can still remove the d phi, dr, d theta here, but this d theta this sine theta cannot be removed due to this d theta. So we'll have to divide by sine theta again, and then there's no r's here to cancel out, so it'll also have to be divided by r squared once again. So plus negative d over d theta, negative k. We can't take away that sine theta. We can take away the d phi, dr, d theta. So we'll get sine theta dt, d theta. And then on the outside there, we're going to have to divide by the r squared sine theta. And then now looking in the phi direction, so this phi here, we have this d theta, dr. This sine theta can be taken out because this is evaluating d phi. We don't have any phi in here. These are all considered constants. So we can take the sine theta out, but it's going to turn into sine squared theta because we're dividing by another sine theta. And then we'll still have the r squared there too, because there's no r's to take away from that term. So we can cancel the d theta, dr, d phi. So we'll get negative d over d phi, negative k dt over d phi, because I'm going to pull that 1 over sine theta out to get 1 over r squared sine theta squared. So that's what that term will look like. So those are all 3 of our net heat flows after canceling out the volume. That's what they end up looking like. And finally, we have to add back our energy generation, which at this point will just be Q dot now that we've taken away the volume. So our next step now is to divide by rho C in order to be solving this equation in terms of changes in temperature over changes in time. So we'll go ahead and do that. We get our dt on the left side now, and we're dividing by rho C, which, as you recall, is going to turn all of our thermal conductivities into thermal diffusivity components. And once again, we can cancel out those double negatives in all of these terms and then pull our k out front for all of these because it is a constant. So cancel all these negatives. Great, great, great. And now we pull that thermal conductivity to the front. K divided by density and heat capacity is going to equal our thermal diffusivity, which is represented by alpha once again. So we have our alpha out front. We have d dr times r squared dt dr times another 1 over r squared on the outside. This is going to have big brackets. And then d theta times sine theta dt d theta times, once again, the 1 over r squared sine theta plus the final phi part, so d over d phi times dt over d phi. That's multiplied by 1 over r squared sine 2 theta plus q dot. All right, so this is this entire equation simplified. We pulled all of our k's out front to turn into the thermal diffusivity here. We can't simplify this into the second derivative due to this r squared, and then that r squared is still from here. And then here, same thing, we cannot simplify this into the second derivative due to the sine squared. This was our leftover here. And then here, we actually could simplify this into our second derivative of phi, because we don't have any phi in here that we have to evaluate first. And then this was the additional from that here. And then on the outside of everything, not multiplied by the thermal diffusivity, is our energy generation term, which is just q dot now. So I'm going to go ahead and rewrite this to make the phi term be the second derivative of phi. Alright, I almost got it on one line, but not quite. So all I did here was rewrite the whole thing and then turn the phi one into the second derivative. Oh, I forgot a squared here. Alright, there we go. Turn that into the second derivative, but the rest of it remained the same because it cannot be simplified further. One last thing is I noticed I forgot to divide the energy generation by density and heat capacity, which is what we did in the beginning. So this, I'll rewrite to have density, heat capacity underneath that one as well. But don't forget that. That's a very important part. So this is our final equation this is our most simplified version of our heat diffusion equation in cylindrical coordinates. So this is our simplified version of that. And now we're going to look at the case where we have steady state, no generation, no heat generation, and only radial direction. So let me rewrite this big old equation one more time before we start simplifying things based on these conditions. So we have dt equals thermal diffusivity d over dr times r squared, dt over dr times 1 over r squared, and then d theta sine theta, dt over d theta. That's times 1 over r squared sine theta plus the second derivative t phi. That's 1 over kind of ran out of room here, but it's okay. So this is our copied over equation here. And now, if we have steady state, once again, that means that nothing is changing with respect to time. So our left side of the equation will go to 0. We also have no energy generation, so we can make that term go to 0. And we only want to look in the radial direction, so we can cancel out both the other directions, theta and phi. Let's rewrite this. 0 equals thermal diffusivity d over dr times r squared dt dr times 1 over r squared. So we can get rid of both the thermal diffusivity and the 1 over r squared because it'll get consumed by that 0. And this will simplify further into 0 equals d over dr r squared dt dr. So we have 0 equals the thermal diffusivity times d over dr times r squared, dt over dr, and then also multiplied by an additional 1 over r squared. So we can get rid of our thermal diffusivity because that will be absorbed by the 0, but we have to keep this 1 over r squared because that is the variable that we're looking at the derivative for. So now we have 0 equals d over dr times r squared dt over dr, all multiplied by 1 over r squared. So this is what we have for our simplified version. And now we're trying to look at how the temperature is changing depending on the radial direction or what radiuses we have. So we're going to have dt over dr equals our equation that we currently have, dt times r squared dt over dr times 1 over r squared. So we're going to bring the r squared to the other side, and we're going to set this equal to c, which is going to be constant. So like I said, we're setting this this whole equation equal to dt over dr because we're trying to find how the temperature is changing in relation to the radius. And all of these are going to be values that we know, so it's going to turn into a constant. And then this r is the r that we're evaluating for in order to find our dt. So let me rewrite this as r squared dt dr equals our constant c. So I've substituted c in for that whole big term, moved the r squared over, sorry. Now we want to get this with like terms on the same side. So we're gonna do dt equals c over r squared dr. So we've set it up this way in order for us to take the integral of both sides to evaluate the change in temperature. So I just moved the dr over and the r squared back over, and now we'll take the integral of both sides. And if you take the integral of dt, that'll just be, actually we need to set our bounds first. I'm getting ahead of myself. So we have put the integral symbol in front of the dt and the dr side, so both the left and the right side. Now we're trying to find the temperature at a final position using the temperature we know at an initial position. Same thing with the radius. The radius of a position we know are not, depending on what we want our final radius to be, rf. So now we can solve, and if we do the integral on the left side, we get tf minus t naught equals, and then if you do the integral of 1 over r squared, it's the same thing as the integral of r to the negative second power. So you raise that 1 power, so r to the negative 1, and then multiply in the front coefficient by whatever the power is. So that'll be negative c over r. Evaluated at rf, r naught. So this is what I have right now. Tf minus T naught equals negative C over R, and then we can plug in these values, so we get Tf minus T naught equals negative C as our constant, and then 1 over Rf minus 1 over R naught. So that's what we get here. Tf minus T naught equals that whole big constant term, negative whole big constant term, 1 over the final radius minus 1 over the initial radius. So now we can multiply this negative in here. We get, I'm just going to turn the Tf minus T naught into delta T because that is what it is, change in temperature. And we get C 1 over our initial now minus 1 over our final because we multiplied that negative in there. Now we can solve for C. We get C equals delta T all over 1 over R naught minus 1 over RF. So that's what we get for our C. And the whole point of solving for that is we needed to find our C to plug back into this initial equation here in order to solve for dt dr. And the dt dr is what we have to plug in for our Fourier's law. So when we look at QR, which is Fourier's law, the heat flow in the r direction is the negative Ka dt over dr. So what we were trying to solve for here is this dt dr term, which we do have up here, but we had to solve for this constant. So now that we have that constant, we can say that dt over dr is equal to our constant, delta t over 1 over r naught minus 1 over rf, times 1 over r squared. Because we have to move that 1 over r squared that's right here, or the r squared over back to this side, to get dt dr equals the constant that we found right here times 1 over r squared. And now we take this and we plug this back into this equation. Once again, we're trying to get this in the format of delta V equals IR, because we want to relate delta V to delta T, I to Q, and find what the resistance is when we're looking at a spherical unit, just the same as we did for Cartesian and cylindrical. So we go ahead and plug in QR equals negative K. Now the cross-sectional area of a sphere is going to be 4 pi r squared. So that's the area of our circle squared, 4 pi r squared. And then plug in the dt dr term that we just derived, delta t, 1 over r naught, 1 over rf, times 1 over r squared. So when we plug in all the terms that we know into our Fourier's law, we can cancel out this r squared here with this one, get rid of that whole thing. Let's simplify that a little bit. QR equals negative K 4 pi times delta T, 1 over R naught minus 1 over RF. All right. So now we have our fully simplified form. We want to solve to get this in the same format as, oh gosh, my pencil's in the way, as this right here. So delta T equals Q, and then whatever we have left else is our resistance term. So let's rearrange this thing a little bit. Delta T equals Q, and now we're going to have 1 over R naught minus 1 over RF all over negative k for pi. So let me double check. Yep. So this entire term right here is going to equal the resistance when we're looking at a spherical object. So we have down here, just reordered it to be in the correct format as the delta V equals IR. And so that whole term right there is going to equal the resistance when we are looking at a spherical system. And so that was what I wanted to teach you all today. So hopefully you enjoyed.